All right, so hopefully you watched video 6.5, the honors video about work and energy. That basically hit most of the concepts that we're going to be, talking about here in 9.1 and 9.2. I do want to fill in a couple gaps that I think were left out by that video. So at this point, as you're doing work and energy problems, here's what your train of thought should be. You should be thinking either, the only work is being done by conservative forces, so my total energy is constant. Okay, that's one type of problem. Okay, or we have non-conservative forces that are doing work, so my total energy is going to change. Those are the two types of problems. Okay, so that when you're reading a problem that deals with energy, that should be your jumping off point, is deciding, is my total energy constant or not? Okay? In terms of problem-solving strategies, you have to identify the important points in the object's motion. Okay? If it's about a kid going down a slide, then you should identify the top of the slide and the bottom of the slide as important points in the motion. Okay? If it's about a spring, a box hitting a spring, then right before the box hits the spring is an important point. Probably when the spring stops the box would be an important point. Okay? And so identify what the energy looks like at each of those points. All right? So, if you haven't already done so, why don't you dig out this note packet. I'm going to kind of run through this because a lot of this is going to be overlapped from what you got in the 6.5 video. But like I say, there are some gaps that I want to fill in. All right, so the chapter 8 stuff, unit 8 was this. We talked about the fact that the work done by a conservative force is equal to the opposite of the change in potential energy. If I drop this pen, gravity does positive work, but we lose gravitational potential energy. Good? All right. Also in chapter 8, chapter 9, in that last unit, nope, I'm wrong, chapter 8, in that last unit, we talked about the fact that if the work done by your non-conservative forces is 0, then your total energy won't change. And we called that a conservation of energy problem. We said that energy is conserved. All right, so what happens if the work done by your non-conservative forces is not 0? All right, and the 6.5 video gives away the answer to that, but it doesn't do a great job of explaining the why. And I think that there's some value in you understanding the why. All right, all right, so when we talk about network, you guys, there's two ways you can write network. You can write it that way, or you can write it this way. Anybody have a preference?
The last.
Latter one? Do this one? Okay, cool. All right, so network. So when we talk about network, there are two ways you can think about it. Okay? You can individually calculate the work done by all of the individual forces and then add those up. Okay? So you could do, the work done by force number 1, plus the work done by force number 2, plus the work done by force number 3. Or it turns out that's the exact same as doing just figuring out your net force and then figuring out how much work is done by that net force. So in other words, net force times displacement. Okay? So, why is that network important? Well, let's see. For simplicity, let's just assume everything's linear here. So I'm going to not worry about the fact that this is a dot product. Let's just do force times displacement. Okay, assuming that everything is, parallel or, I guess, anti-parallel. Follow? Okay, so if we say that net work is net force times displacement, then watch what we can do. I totally didn't give myself enough room here. Okay, so net force. What's net force? Newton's second law. Mass times acceleration, right? So I'm going to replace net force with mass times acceleration. So I get mass times acceleration times delta x. So this is still net work, right? Everybody good? Yep. All right, now this we know is a thing. 2 A delta x equals VF squared minus VI squared, right? So if we divide by 2, we find that A delta x is 1/2 VF squared minus 1/2 VI squared. Huh. Oh. All right, so now we've got mass times 1/2 VF squared minus 1/2 VI squared, right? What is that? If I distribute the m's, you get 1/2 mVF squared minus 1/2 mVI squared. That's the change in kinetic energy.
Did they derive that formula from doing this backwards? What you just did backwards? The energy, you say is change in energy and then towards the.
Gotcha. I don't know the answer to that. Like the original.
So we say network is change in energy, so we do KE minus KE and then substitute 1/2.
Right. Yeah. I mean, I don't know I don't know which direction they came at it from, but. Okay. So when it says this is the work energy theorem, it means this: net work is change in kinetic energy. So that is a very well-known theorem. It's called the work energy theorem, sometimes the work kinetic energy theorem. Yeah. Right. All right. Everybody good? All right, so this is big. You absolutely need to know that. All right, so it turns out we can then use that to figure out something about the work done by non-conservative forces. All right, so far here are the two things that we know. We know this from Unit 8. The work done by conservative forces is the opposite of the change in potential energy. And we just learned the work energy theorem, right? All right, so let's see. So do you guys agree that, so net work is the total of all of the sort of individual works, right? Oh, sorry, you guys said you wanted the sigma. Okay. Sigma, W, there we go. Okay, so net work, shouldn't that just be equal to the work done by conservative forces plus the work done by non-conservative forces?
Yeah.
Right? I mean, all of our forces are either conservative or non. So we ought to be able to find the total work by just adding up the work done by those two categories of forces. Follow? All right, so let's do a simple substitution here. So let's see, net work, this is change in kinetic energy, equals, let's see, the work done by conservative forces is negative change in potential energy plus the work done by non-conservative forces.
Oh,
Everybody good so far?
Just one question.
Yeah, shoot.
Let's say I was raising a ball up in the air, right? Aren't you doing work, but you're not gaining kinetic?
Let me finish this, and then I'll do an analysis of a real simple example.
Okay.
Okay, so everybody good up to here? This is a plus sign if you can't read my copyright. All right, so I don't like this negative. Let's move it to the other side. So I'm going to add the change in potential energy to both sides. So change in kinetic energy plus change in potential energy is change in total energy, right? Because all of your change in energy has got to be either kinetic or potential, right? Oh, that equals our work done by non-conservative forces. It's really funny, isn't it?
It's hilarious.
All right, this theorem doesn't have a name, but it's important. All right? In fact, I would almost argue I use this almost like any time you're dealing with a problem where your energy is changing due to non-conservative forces. I use this way more than I use the work energy theorem. Okay? I find this to be very, very useful. Okay? Yes, sir.
Motion to name it the Keeper theorem.
All in
favor? Motion.
Nice. Oh, all right. Okay, moving on. I like that though. All right. So is everybody good? Okay. Now, so let me come back to Zach's question. All right. So in honors physics, when we went through this stuff, I started out with a real simple example. So let's suppose we're just lifting a box, all right? So, I don't know, whatever. Maybe it's a 5 kilogram box, and maybe I'm going to lift it up, say, 4 meters. Okay? So usually when you lift a thing, you assume that it starts and ends at rest, right? Like, I'm going to take this thing and put it on a shelf. It started at rest, it ended at rest, right? Okay? And so the idea is gravity is going to be pulling this down with a force of 5 times 9.8, so 49 newtons, right? And then to lift it, how much force would we need? So technically speaking, the force of U to get it moving would have to be a little more than 49 newtons, right? I know, it never stops being funny. So technically to lift it, the force of U would have to be a little more than 49 newtons, right? Then to keep it moving, your force would be exactly 49 newtons. But then to stop it at the top, you'd have to use a little less than 49 newtons, and it kind of averages out, right? So you can find your work by multiplying your average force by your displacement. Your average force is just going to be 49 newtons, right? Good? All right? So, up here at the top, what we know is our height is 4 meters, our velocity 0. Down here at the bottom, our height is 0, our velocity is 0. Okay? So let's take a minute. So, my GPE here is going to be 0. My KE here is going to be 0. My total energy here is 0, right? Follow? All right, up here at the top, my GPE is going to be mgh, which I think is 196 joules. My KE is going to be 0, which means my total energy is 196 joules. Everybody good? All right, now let's take a second. There's only 2 forces in this problem, so let's calculate the work done by all of the forces. All right, so the work done by U should just be the force of U times the displacement. Right? And the work done by gravity should be the force of gravity times the displacement. So, a lot of 196s on the board. So, let's see if we can figure out what this all has to do with these little rules that we've learned. Alright, so, let me get a new color pen here. How about purple? Okay, so, one of the things we learned was this, that the work done by conservative forces is equal to the opposite of the change in potential energy. So relate that to this problem. Sure, we got here. Yeah, let's see, my potential energy went from 0 up to 196. So I gained 196 joules of potential energy, and the work done by gravity was negative 196 joules. Check, check, it works out, right? All right, we also learned that the net work is equal to the change in kinetic energy. What's the net force? What's the net force? 0, right? Basically, right? It averages out to 0, certainly. Right? So if your net force is 0, what's my net work? 0. How much did my kinetic energy change by? 0. It started and ended at rest, right? Okay, so that's what you were asking about, right? Okay? Now, so then the last thing is the work done by non-conservative forces. That should equal our change in total energy. What's the only non-conservative force in this problem, you guys? U. How much work did you do? 196 joules. How much did my total energy change by? 196 joules. So all of the work that you did was done to give this thing energy it didn't have before. It turns out in this circumstance that you did exactly as much work as gravity, so you didn't change the kinetic energy, you just gave it gravitational potential energy.
And you did positive force.
Yes. So there are 2 reasons, and you should be familiar with both of them. There are 2 justifications for that statement that we did positive work. Give me one of them.
I know that it's going with the motion.
What's going with the motion?
Your force.
Good. Your force and the motion are both
What I don't
up.
understand is if it's the opposite of potential, changing potential energy is getting increased.
So, what was your original question? You said,
Positive.
is what positive?
Your work.
Your work, not gravity's work. Your work.
Right.
So your work, you're looking at, in what you just said a second ago, you were talking about gravity. So you were looking at this. That has nothing to do with your work.
Oh, it's not conservative.
Right, your work is non-conservative. That's this guy.
All right.
So your work is non-conservative. Well, your force is non-conservative. Follow?
Yep.
So your work is positive 196. The change in total energy is positive. Follow?
Yep.
Everybody good? All right, so a lot of the concept-y problems on this homework assignment deal with just manipulating these three equations here. Okay? In particular, there's a problem on this worksheet. I think it's, shoot, I'm going to have it handy. Yeah, number 7, the very bottom of the front page. I don't know if you guys remember, we've seen this problem before, and I said, oh, shoot, we shouldn't have done this yet. We haven't learned it yet. There's a really easy way to do number 7 in one step. Like, you can almost do it in your head, okay? By thinking creatively about these three equations, all right? And as a hint, you don't need the angle or the magnitude of the force at all to solve the problem. Okay, you can do it that way, and I think Jacob showed us a cool way of doing that before. But there's a really sort of simple, direct way of doing it using these things. All right? Questions? All right, finally, the last thing is friction. Where does friction fit into all of this? All right, this was not in the honors video. All right? So, I don't love the way that this is always presented, but so if you rub your hands together, they get hot, right? Mm-hmm. Okay, so what you're doing there is you're converting kinetic energy, right? But then the friction resists that kinetic energy. It works against the kinetic energy, creates friction, which then creates heat, right? Okay? So a very simple explanation that is often given to explain the energy loss due to friction is this. The work done by friction is the opposite of the change in thermal energy. In simple terms, imagine a baseball player sliding to a stop. So everybody point for me. With the baseball player is moving this way, right? Which way is friction? That way, right? So the baseball player is going to lose energy. In other words, friction is doing a negative amount of work, right? So we're losing energy, but gaining thermal energy, right? The work done by friction is negative, and so we're gaining thermal energy. All right? So there are a few questions on the worksheet. Before you go real quick, what do you have this hour? With McGuire? Sorry? Mr. Kim. Okay, so I need to email Mr. Kim. There's no way I'm going to remember to do that. Sophia Ruzanowski. Yes?
So what's gaining the thermal energy?
Oh, really, really good question. Dan just asked a gazillion-dollar question that I should have included in the notes. Dan just said, what's gaining the thermal energy? When you rub your hands together, does just one of your hands get hot? No. They both get hot. So it's thermal energy gained by the system. Okay? When this baseball player slides across the ground, the heat is gained by the baseball player Earth system. Does that make sense?
Yeah.
Really, really good question. I'm super glad you asked that. All right. Does that make sense? Okay. All right. So, honest question. I've got a couple examples prepared here. And I more and more am struggling with how helpful it is when I do these examples as compared with you just trying to do the problems, you know? Because as I've said a couple times, there's no way that I can prepare you for every example you're going to see on the homework, you know. So I've got an example here. It deals with work of non-conservative forces. There's some elastic potential energy here. Would that help you get kind of a start? Yes? Okay. All right. So let me run through this. And I will, try my best to kind of model what I see as how you should be solving these problems. Okay? So again, to reiterate, when you solve these problems, you absolutely need to be identifying the important points in the motion of the object. Okay? Give them names. Call them point A and point B. Or, Roman numeral 1 and Roman numeral 2 or whatever. And then write a statement that says, either total energy at A equals total energy at B, or maybe not. The change in total energy between A and B is equal to the work done by the non-conservative forces. All right? So with that in mind, let's run through this and see what we can do. So we've got a 3-kilogram box that's being launched up an inclined plane by a spring. So we're going to kind of like squish this thing, let it go, and the block is going to shoot up the ramp. Okay? So here's what we know. We know that the mass is 3 kilograms. We know the plane is inclined at 30 degrees. Coefficient of kinetic friction is 0.25. Spring constant is 800 newtons per meter. A says if you press the block against the spring to compress the spring 0.2 meters, then how much work are you doing? Okay, so I guess to be fair, this probably should have been worded a scotch differently. Let's do this. So let's assume that you're compressing at 0.2 meters from its relaxed state. Otherwise, this gets a little bit more complicated. Well, one step more complicated, I guess. Okay, so it says if you press the block against the spring to compress the spring that far, how much work are you doing? So we need to identify the 2 points in the motion that we care about. So there's, sort of this relaxed point before we squish it, and then we squish it. How much energy does it have now, right? So I don't know. You almost need to draw 2 separate drawings for this one. So there's this. And then there's that. Does that make sense? Okay, so let's call this point R as in relaxed, and let's call this point B as in bottom. Does that make sense? All right. And let's see, the 0.2 meters represents how far the block got squished between the relaxed state and the bottom, right? Follow? And this is 30 degrees, right? Everybody okay? All right, so for my relaxed state, did not give myself enough room to work here. All right, so at the relaxed state, so we need to be thinking now about 3 different types of energy. What are the 3 types of energy I need to think about? EPE, GPE, and KE, probably, right? Okay, although I think it seems like the velocity in both of these points is 0, right? Right? It starts at rest, then you squish it and hold it at rest. So the velocity at both of those points is 0. All right? So my velocity here is 0, that means my kinetic energy is going to be 0, right? Let's see. Elastic potential energy depends on how much the spring is squished, right? So in this relaxed state, how much is the spring squished? 0. That's important because that means that my EPE is going to be 0, right? Follow?
Is that the relaxed?
Sorry?
Is that the relaxed one? Is point B?
No, that's
R.
all.
This is
Oh, that's
R.
for R.
Sorry,
I
yeah,
said
there's
that.
R.
My bad.
Cool? Sorry about that. Like I said, I did not do a great job budgeting my space here. All right, so what's the last variable I need to be thinking about? V for kinetic energy, X for elastic potential energy, and GPE, which depends on height. So what's the height here in this relaxed drawing? Is it 0? It's whatever this vertical side of the triangle is, right? So it's a 30, 60, 90 triangle, so it just turns out to be 0.1 meters. Follow? Okay, so the height is 0.1, so I can find my GPE. So you're going to get, what, 0.294 joules? Yes. Oh, no, 2.94. My bad. 2.94. Sorry about that. All right, is everybody good there? All right, so that means that my total energy when it's sitting at that relaxed position is 2.94 joules, right? Cool? All right. I got to erase. All right, now, when you get to this bottom point, velocity is 0, so my kinetic energy is going to be 0. My x is now, what? 0.2 meters. So I can find my EPE, right? By just doing 1/2 kx squared. Yeah, I guess technically it would be negative. I feel like down the ramp would be negative. Sure. It's going to get squared, though, so it ends up not being an issue here. But yes, I agree. Let's put the negative in, because the force is going to be positive. So yeah, we should keep track of that, I guess. All right, so let's see. So we got 400 times 0.2 squared. So you get 16 joules. Uh-oh. My answer's totally wrong. All right. Okay, everybody good up to there? All right. Shoot, I'm wondering how I did that. Because I just reworked it the other day. It's weird. 1/2 k times x squared.
Yeah.
Oh, no, my answer's not wrong. Ooh.
Oh, friction.
Friction. Okay. All right. What's my height at point B? 0. And my GPE then is 0. So that means that my total energy here at point B should be 16 joules, right? All right. So, if this had been frictionless, then I would be the only non-conservative force, right? And so, the work that I did would just be the difference between these. So, whatever that is, 13.06 joules, right? Okay? But there's friction. Does that make sense? All right, so we need to figure out how much work friction did. So I'm going to cave and do this. Sorry. All right, so this, just so you guys know, I'm going to try to be consistent. W with a lowercase f means work of friction, not work final. Here, let me do this. Kinetic. Maybe that makes it clearer. Cool? All right, so here we go. We got a 0.3 kilogram box. No, we don't. We have a 3 kilogram box. My bad. It is recording, I think. I guess at this point it doesn't make much sense to start it, but yeah, it's fine. Okay, so our FG parallel here ends up being, is it 14.7? 3 times 9.8 is 29.4, yeah, 14.7 joules. Perpendicular is 29.4 times the cosine of 30, so this gives you, let's just, everybody good up to there? All right, And then we know our coefficient of kinetic friction is, what was it, 0.25? So that means that my force of kinetic friction is 6.37 newtons. Now, important to make sure you guys understand. Why did I make friction going up the hill? Because between our relaxed state and the bottom, we're pushing it down the ramp, right? Does that make sense? All right, now, there is technically one other force in here. Well, what's the force I'm missing? Air resistance, yes, obviously.
Was that conservative or no?
Air resistance is non-conservative.
Because it depends on the
Because
mass.
it depends on, exactly, it depends on that. You, right? Aren't you pushing it? Right? You're pushing it down the ramp, right? So there's also the force of U. We don't know what it is, though. We can figure it out if we wanted, but... Oh, and the spring. Very good. Oh, yeah, there's also the force of the spring. Ew, this is ugly. And increasingly ugly because the force of the spring is not constant. Which means that the force of U is not constant, and this gets ugly. Okay? So you look at this and you go, but it turns out that it doesn't matter. Because the force of friction is constant, isn't it? So I think we can find the work done by friction by doing the force of friction times the displacement. So 6.37 newtons times, how far did we squish the spring? 0.2 meters. One of those needs to be negative. I'm thinking, like Josh said, let's make the displacement negative. Or I guess it was Josh. Zach, what's your name? Sorry. All right, so this gives you what, 1.274 or something like that, joules. Good? Negative, right? Cool? Questions? All right, so any problems with what we've done so far? All right, so here's what I mean about finding creative ways to use these equations. So let's write down, let's kind of summarize the stuff that we know. So here's what we know. We know that the work friction did is negative 1.274 joules. We know that the total energy in the relaxed state is 2.94 joules. And we know the total energy after we squish it at the bottom is 16 joules. And what we want to know is how much work you did. So, what do friction and U have in common? They're non-conservative forces, right? So let's see. The work done by non-conservative forces is our change in total energy. So that means that the work done by friction plus the work done by U has got to equal final minus initial. So I want bottom minus relaxed, right? Follow or no? All right, so here's the deal. We know that the work friction did is negative 1.274. We're trying to find the work that you did. Total energy at the bottom is 16. Total energy at the top was 2.94, and solve it. And the work that you did ends up being, what, a little more or a little less than 14 joules? Somewhere right around 14 joules. Does that make sense, you guys? Yeah. All right, and at the heart of that whole thing, despite the fact that there are a gabillion numbers to keep track of, is this. All right? I like this problem for a lot of reasons. I'm glad we actually decided to go over it. One, most of the homework problems will usually only have one non-conservative force. Okay? But this is as bad as it can get, right? Like we had inclined planes, we had springs, right? Like there's a lot going on here. Okay? I don't know. Questions with it? All right. So, that was part A.
What's
All right. Part B, if you release, this one's not quite as bad because we've done a lot of the legwork. Part B, if you release the block, how far will it go up the ramp before stopping?
There's still friction.
Still friction. Okay? So here's our drawing. Here's our block at the bottom. The total energy here is 16 joules, right? If you release it, if you let go of it, the spring is going to go ka-chunk. It's going to go through the relaxed state, and it's going to keep going up the ramp until it gets to some point up at the top where it stops. So let's call that point S, as in that's the point where it stops. Cool? Now, if there was no friction, what would be the true about the total energy at that point where it stops? It would still be 16 joules, right? But it's not, right? But I do know that the total energy here is equal to, not in numbers, but in words. What's the total energy they're equal to? Just GPE, right? Which is mgh, right? At the point where it stops, right? All right, and then what should be true about the difference between these two quantities?
The work.
It would be 0 if it was frictionless.
That's the work done by friction.
The difference between these should be the work done by friction, right? Does that make sense? Okay, so let's see what we can do with that. So I know that the work done by friction is equal to mg times the height where it stops minus 16 joules, right? Good? Do I have that right? No, that's right. Because the work done by friction should be negative.
Oh, yes, okay.
And we're losing it, yeah, so we're good. Okay, so obviously I can plug in my m and my g. Let's see if we can do something with the work of friction. So, what do you got, Anthony?
Well, like you know your force, and so then if you do the distance, and then you just do like the sine of 30 times that distance.
So let's call this green distance that I just marked off, let's give that a name. Have we used d for anything yet? So let's call that d. Cool? All right, and we know the work done by friction is the force of friction. Let's see, what was our force of friction? 6.37 was our force of friction, right? So, I've got negative 6.37 newtons times d equals mass times 9.8 times the height where it stops minus 16 joules. So now I've got two unknowns there, the distance it goes and the height that it stops at. So I'm going to give everybody a second to think, because there should be a fairly clear connection between that distance and that height, I think. Yes?
Give me an angle.
Right, there's our triangle, right? Here's height, here's d, here's theta, right? So we're trying to solve for d, right? So height is d sine theta, is that right? So plug in d sine theta and then solve for d. Make sense, you guys? Bless you.
Thanks.
Bless you.
Thanks.
All right. So the fact that our force of friction is constant makes it a little bit easier to work with that force. So
Plus, thanks.
that's a common trick. Oh, well, no. I mean, only if your coefficient of friction was variable for some reason, or your normal force was changing for some reason. All right, are we good, you guys? All right, I think C and D is kind of more of the same. I don't know if there's a ton of value in doing it. Oh, question D asks about heat energy. When I ask you for how much heat energy is created, what am I really asking you? How much work did friction do, right? Okay. So C and D, I don't know that there's anything that we need to, that it's kind of more of the same.
Oh, wait, just my correct question.
Yeah.
So when it asks for the heat energy that, and it like doesn't say magnitude, should we put, like, should we make sure to put the opposite of the work done by friction? Or with like,
If it doesn't say magnitude, I guess I would watch your signs. And I don't know that your heat energy would ever be negative. Right? Because friction is always going to make stuff hotter, so you're always going to be gaining thermal energy, right?
but you could be like, if he was talking about like, how much energy does the, like, I don't know why I never asked that.
Say that again.
Like, when it asks how much heat energy does the object in which friction is acting upon gain, then it would be negative, right?
That would be losing heat.
Yeah, so if it asks how much it gains, then it would be negative.
Why would we use that for?
I don't know, I just, that's why I was.